Wait for 3 seconds. Good morning, friends. In the last session, we have explored the rich set of operators in Java language. We have explored arithmetic operators, and then we have discussed the bitwise operators. In bitwise operators, we have seen AND operator, OR operator, NOT operator, ones complement operator, then XOR operator. Then coming to the bitwise left shift operator, less than operator. This is said to be the bitwise left shift operator. Apparent then operator a number of times, because left shift operator, this is a binary operator. The apparent is performed the bitwise left shift operation for the specified number of times. That is the meaning of this bitwise left shift operation. We have seen this example, byte x is equal to 1. Then performing the bitwise left shift operation on the byte variable 1 time, 2 time, 3 time, 4 time, right? Any number of times. We have discussed how the results are coming when we perform the bitwise left shift operation. For example, here the byte variable is assumed, x is assumed the value 1, byte x is equal to 1. I explain in detail. Look here. Byte x is equal to 1. How to represent x in a 8-bit register, because x is a byte variable. Storage representation of x in the binary encoding means 0, 0, 0, 0, then 0, 0, 0, 1. This is the encoding of a binary variable x. Now let us try to find the value of these things for each shift. How the value of the left shift operation is going to be affected on the variable x. Suppose shift j is equal to 0. Or let us form the table shift using the control variable g. Then writing the value this expression byte of x less than g. Let us explore this case for different values of g.
Sir, your voice is not audible, sir.
Sir, your voice is very low, sir.
Already. 1 minute. Let me check. Check it now. Is it okay? Is it audible?
Yes, sir.
Okay.
Sir, it is audible, but it is very low,
Now
sir.
considering the variable. Okay, 1 minute. I check it. I work in a college, right? I set correctly settings, microphone settings. Okay. Maximum volume has been set. For me, it's not a problem. Okay, I consider a byte variable. Byte x is equal to 1. In this case, the variable x is represented in this format. 7 zeros followed by 1. Because byte occupies 1 byte in the 8-bit representation, 8 bits representation, x is represented like this. Now, initially, right, assume the value of shift is 0. When shift is 0, right, we are performing the value byte of x less than j. 0 times you are performing the shift. So, what is the value? 7 zeros followed by 1. Then shift number 1. In this case, what is the MSB? Most significant bit. 0 is the most significant bit. 0 will be lost. So coming to the next bits, sequential bits from 2 to 1, 2, 3, 4, 5, 6, 7, 8, right? The 8th bit is lost. So from bits 1 to 7 are moved here. Then what about the new LSB? Gives a significant bit. 0 is added. Here MSB 0 is lost and new LSB is a significant bit. 0 is added. Now in the second shift, shift number 2, twice we are performing the bitwise left shift operation. So in this case, what happens? Already we have performed bitwise left shift operation one time. This is the result. If you perform the bitwise left shift operation on these bits one more time, what about this MSB? Most significant bit. This will be lost. So having the remaining 7 bits here, 7 bits are moved here. And what about the new LSB? Leaves a significant bit, newly added to a value 0. Next, shift number 3. In shift number 3, this MSB is lost. Then these 7 bits are moved one position left direction. Now new LSB 0 is added. Here also same explanation. MSB 0 is lost and the new LSB 0 is added. Next stage, shift number 4. In shift number 4, what happens? This 1 is moved to the next bit position. This is 0. New LSB 0 is added. Next stage, shift number 5. In the 5th shift, this 1 is moved to this position. New LSB 0 is added. And in the 6th shift, what happens? Shift number 6. This is 0. 5th position. Then 1, 2, 3, 4, 5, 6, 6th position. Now 7th bit has been set to 1. And in the 7th position, 7th shift, what happens? Here this is 7. MSB, new MSB is set to 1 here. Remaining bits are zeros, including the LSB. New LSB 0 is added. Now this is actually the value 1. Next stage, this is a value 2. Then this is a 4 multiplication by 2. This is 8. Likewise, this is 16, and here 32, 64. Here the value is 64. Then what about here? What about the value of byte of x less than j during the 7th shift operation? Can you say what is the value of this one?
128.
This is equal to
128.
128. But actually, but actually 128 will not be stored in a byte variable. Because what is the range of byte? Minus 128 to
Plus 127.
127. This is a range. Yes. So 128 will not be stored in the byte variable. Actual value of this one is 128. So byte of 128, this will not be stored. In this case, Java uses a 2's complement encoding to represent the negative numbers. Now in one followed by 7 zeros. MSB most significant bit is 1. This is the indication of a number is a negative quantity. So this one significance, right, I am highlighting, please check that. MSB1, this is the indication of a negative quantity. This means that remaining 7 bits are available in which format?
2's complement.
Remaining 7 bits, right, 2's complement format. So you need to decode remaining 7 bits in a 2's complement format. So decoding remaining bits in a 2's complement format. What is 2's complement? What is its 2's complement? Converting zeros into ones. 7 ones plus 1. Now what happens? This is you see 1 followed by 7 zeros. 1 followed by 7 zeros. This is represented as what is 1 followed by 7 zeros? Just now we have written 128. What is its sign?
Minus 128.
Minus 1. Hence the quantity actually decoded is the value of 1 followed by 7 zeros, which are represented in a 2's complement is actually minus 128, not plus 128. You should understand very carefully. So in the 7th shift operation, the value of byte of x less than j becomes 128. Then continuing in the 8th shift operation, I write here shift number is 8. In this case, just consider this quantity. What is the MSB? MSB is 1. In this stage, performing a bitwise shift left operation, MSB will be lost. So 0, 0, 0, 0, 0, 0, 0. New LSB 0 is brought. This results in the quantity 0. So subsequently, we can perform any number of times. The result will be 0. For all the remaining shifts, result will be 0. Understand or not? Say yes or no. Java C operators spider Java. Java operators 5. We have to look into this expression alone. Byte of x less than 1 or 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Then 30 and 31 are given. Now this is the result of byte of x less than 1, right? First stage. The result is multiplied by 2. Then second shift, third, fourth, fifth, sixth. This is the result. Y is equal to minus 128 during the 7th left shift operation. Have a look into here. During the 7th bitwise left shift operation, the value of byte of x less than j becomes minus 128, not plus 128. Understand or not? Understand? Then in the next
The
bitwise
most
shift
significant bit.
operation, y becomes 0. Most, what is your query?
Sir, whenever the most significant bit is 1, then it is stored in the 2's complement form only, sir. Any binary digit, if the most significant
Yeah.
bit is, then the number will be stored in a most significant form.
One, then it is it is represented in a 2's complement format. So for this highlighted number, you need to find out the decoded value of 2's complement format. So representing, right, this is manually, right, minus of, since MSB is 1, and finding its 2's complement, you have a quantity 128. So actual value is minus 128. Hereafter, you can perform any number of bitwise left shift operation on this byte variable, right? In all occurrences, the value of left shift operation becomes 0. This is the case when you store the quantity 1 into a byte variable. Suppose if you want to store the result into the integer variable, right? Suppose byte x is equal to 1, a is equal to x less than 1 means in this stage x is a byte operand and 1 is the integer operand. The expression is entirely converted to the integer mode. In this case, you need to consider the variable a, right, which is in the form of integer mode. So integer mode means here consider this in 4 bytes format. Int a is equal to 1. How to represent a is equal to 1 in the 32-bit register? 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is the value of A stored in the 32-bit register, or the variable is int A. Int A is equal to 1. Now for this, let us try to find out the, say, bitwise left shift operation. Shift of J, we are directly performing without any type casting. Suppose A less than J, or assume int x is equal to 1, whichever is. Here x is less than J. Shift is, for example, 0th shift. In 0th shift, what happens? There is no change in a variable x. This is a value of x. Then in first shift, what happens? This becomes 0, 1 becomes 1, 1, 0. Then in the second shift, this is 1, 0. The second shift, this becomes 1, 0, 0. Then third shift, every stage MSB is lost and a new LSB is added. 1, 2, 4, 8. Then in the fourth shift, this becomes 16. Understand carefully, the 0th shift, 1 is available in the first bit position. First shift, what happens? 1 is available at the second bit position. Fourth shift, 1 is available at the fifth position. So I do not want to continue this. Let us generalize. During say the 20, or you can say, right, 30th shift, what happens? In 30th shift, what happens? Which bit is set to 1?
35.
Ith shift, I plus 1 position is set to 1. 30th shift, 31st position. What is 31st position? This one, am I right? All bits are set to 0. Then carefully consider the 31st shift. In 31st shift, what happens?
32nd bit to first
New
one value.
MSB is set to 1 during the 31st shift. Okay. Last bit is 0. This is 0. Now, these are the values, right? You can easily find out 1, 2, 4, 8, 16, 32, 64, etc. Right? Here, right, you will have the maximum value of, for example, this will be 2, 1, 4, 7, 4, 8, 3, 6, 4, 8. This is the value of this quantity. But actually here, as we discussed earlier with respect to byte value, here what happens, MSB is 1. This is actual value, this one. What is MSB? MSB is 1. This MSB is 1. This indicates that the remaining bits are available in this 2's complement format. So to find out the equivalent integer, what you have to do is decode it using 2's complement. So finding a 2's complement of which one? This entire quantity. Remaining 31 bits, excluding the sign bit. Can you say what is its 2's complement value? All 31 bits are set to 1.
Minus 2, 1.
Yeah, all 31 bits are set to 1. Yeah. Then what will you get means you will get this quantity. This is the actual quantity, 2's complement. Now this is equivalent to a quantity 2, 1, 4, 7, 4, 8, 3, 6, 4, 8. So actual value of this one is encoded in a 2's complement format. MSB most significant bit is 1, its sign is minus, so minus 2, 1, 4, 7, 4, 8, 3, 6, 4, 8. The range of integer, right? Minus 2, 1, 4, 7, 4, 8, 3, 6, 4, 8, 2 plus 2, 1, 4, 7, 4, 8, 3, 6, 4, 7. So during the 31st shift operation, the value of integer variable x is set to do this quantity. And check it in the output. Here write 2, 4, 8, 16, 32, 64, etc. Have a look into these lines. This is during the 30th operation, right? During the 30th operation, and the quantity 2, 1, 4, 7, 4, 8, 3, 6, 48 is solved, right? So you can get this quantity. Then the last line, a is equal to x less than 31. 31 times we are performing a bitwise left shift operation on the integer variable x. Then you are printing the value of a, right? So the value of a is a negative quantity. Minus 2, 1, 4, 7, 4, 8, 3, 6, 48. Understand or not? This way Java performs the bitwise left shift operation. If you have any queries, you can ask. Having any queries? So higher order bit is shifted out, a 0 is brought on the LSB. For the integer operand, bits are lost once they are shifted bit position 31. So after 31, right, if you try to perform one more time means, right, you have to carefully understand how the MSB is going to be lost and what about the new LSB. You try to check the code. Then in case of long operand, after 63rd bit position, then 64th is actually the MSB for sign bit position. So we will be lost in the corresponding bits. In case of negative numbers, right, byte or short value, right, what will happen means performing the bitwise left shift operation, sign will be extended. You check it in the next example I show you. You try to perform the same thing, right? This is right shift operator. You try to take one negative quantity and perform the bitwise left shift operation. The corresponding sign will be extended. You try to check it. Then the next operator is right shift operator. Right shift operator takes this general form. Operator is greater than operator. Operand greater than number of times. Similar to the bitwise left shift operation, you need to perform the bitwise right shift operation with respect to greater than operator. Only thing in the bitwise right shift operation is this operator retains the value of MSB in each right shift operation. That's what this operator is said to be sign extension operator, which extends the sign for negative numbers because MSB is 1. 0, no problem, right? You will be saying right to 0. 1 means each right shift operation brings the same value of MSB. For example, consider this code. Int x is equal to 2 1 4 1 4 8 3 6 4 7. Int j is equal to 0, j less than 32, the j plus plus. How to represent this quantity? 2 1 4 1 4 8 3 6 4 7 in a 32-bit register. Previously we have written this is the actual value 2 1 4 1 4 8 3 6 4 8. Similar to that, right? 1 2 that is 2 for 0, 2 for 1, 2 for 2, 2 for 3, 2 for 4, etc. This is 2 for 32. You need to find, right, the equivalent binary encoding to represent this quantity 2 1 4 1 4 8 3 6 4 7. J is equal to 0, j less than 32. So 32 times, right, we like to perform the bitwise right shift operation. Since this is a positive quantity, so what is its MSB? MSB will be 0. MSB is clearly 0. Since x is positive 1. Since x is a positive integer. Each bitwise right shift operation divides the actual value of a variable by 2. Suppose as 16. 16 means what happens here, for example, 0 0 0, then 1 0 0, 1 2 4 1 2 4 8. 16 means here 1. Consider this as a byte variable. Performing bitwise right shift operation, uh, these digits, first 7 digits, are moved to digits from right at this position to this position. What about the new MSB? New MSB is 0, right? That means MSB is retained. That's the meaning of sign extension. Sign is extended. Now the quantity 0000140 has a value 16. 1 2 4 8 16. Then here, after performing one step bitwise right shift operation, this becomes 8. Then if you perform one more time, what will happen means here this 0 is same as this 0, and keeping the remaining 7 bits here, what happens? This becomes 0 and this becomes 1. Actually, right there, these 7 bits are moved here. This becomes 1 2 4. Division by 2. Same as the C in the C++ languages. Bitwise right shift operation performs division by 2. Bitwise left shift operation performs the role of multiplication by 2. So first check the result of the first part. Java C operator 6.java. Yeah, this will be commented out. So, slash star slash. Compilation is okay. Then running the code. Java operators. Let's consider the first purpose. Here, what is the code? The value of j is printed. J ranges from 0 to 31. Since j is less than 32, we do want to find out the quantity x greater than j. So, initial value of j is 0. 0 times performing bitwise right shift operation, no change. The same value of integer variable x is. Then j becomes 1. This is halved, right? Divided by 2. X is equal to 2, 3, 4. Every stage, the value of integer variable x is halved. During the 30th position, right, you are getting a value 1. Then in the 31st right shift operation, what happens means, since previously you have the LSB, least significant 1, that 1 is lost. So during the 31st right shift operation, the quantity 1 becomes 0. Understand or not? Likewise, the quantity int y is equal to -2, 1 4 1 4 8 3 6 48. This is performed bitwise right shift operation for 31 times. Now, how to represent this quantity in integer variable? What is the value of y or encoding of this one? Just now we have seen in the previous example, right? 1, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Lost by 1, 2, 3, 4, 5, 6, 7, 8. 4 plus 4, 8. This is the actual value of -2, 1, 4, 1, 4, 8, 3, 6, 48. Because what is the MSB? MSB is 1. 1 is the indication of a negative number. Then remaining bits are encoded in a 2's complement format, right? So finding the 2's complement or decoding the 2's complement equivalent, right? You will be getting the value 1 followed by 31 zeros. So you will get -2, 1, 4, 1, 4, 8, 3, 6, 48. This is a representation. Now we are performing the bitwise right shift operation for 32 times. Here, control C. During the value of j is equal to 0, we are having this quantity. When j becomes 1, what happens? Bitwise right shift operation, m must be 1, right? This 1 is moved to 1 bit position right. So what about the new MSB? What about the new MSB?
0.
0.
Not 0. I said MSB is retained sign extension. The operator is to be sign extension operator. Sign is extended automatically when you perform bitwise right shift operation. This is a different operator. So the sign is 1. 1 is retained here. I wrote 1 here. 1. Okay, having 32 bits. Now understand clearly, this 1 indicates that this is a completely a negative quantity. Now try to find the 2's complement equivalent. What is the 2's complement of this highlighted number? Very simple question. What is the 2's complement of this highlighted number?
Sir, same number.
Yeah, very good. Same number. Because right, you need to check it from right to left where the first one is. From right to left direction, the first one is here, right? So you need to keep the number as it is. So here, this is the 2's complement equivalent. Carefully understand that the MSB1 indicates a negative quantity. This highlighted number should be decoded in a 2's complement format. So decoding this into a 2's complement, you will get a value 2 147 483 648 divided by 2. So you have this result. What is that one? 107374184. Sign is minus because the MSB is 1. Understand or not? Likewise, in the next shift, when J becomes 2, what happens? Keeping from a split position, LSB is lost. New MSB, that is 1, sign is extended. Now this value is, right, 1 indicates a negative quantity. Now decode this highlighted sequence in 2's complement format. So from right to left, you try to see where the first one is. First one is available at this position. I think this is the second one, right? First one here. You keep all these string sequence as it is, and before that, right, one is there, one is converted into 0. So actually, this is the 2's complement of that highlighted number, and this one indicates a negative quantity. So the equivalent value of this highlighted one is the previous value divided by 2. Previous value is this one 107 something. That is divided by 2 536 something, right? This is the actual value. This is the case when J becomes 2. Let us generalize. Can you say what will be for J is equal to 31? J is equal to 1 means here what happens? 2 ones are there. J is equal to 2 means how many ones are there? 3 ones are there. So when J becomes 31, what happens? Not to generalize, 4, 5, 6, 7,
All are
8.
one.
1, 2, 3, 4, 5, 6, 7, 8. Yeah, all bytes are set to ones. 1, 2, 3, 4, 5, 6, 7, 8. So when J is equal to 31, this is the quantity. Now what is its equivalent value? What is the value of all ones which are represented in the 32-bit register? What is the difficulty in this? I said
Sir, minus one, minus one.
when
Minus
you
one.
use 1.
One, sir.
Very good. Yeah, very good. MSP is 1. This is the indication of a negative quantity. Negative quantity. Remaining bits should be decoded in 2's complement format. So finding the 2's complement of the remaining bits, converting zeros into ones, ones into zeros, then adding 1, we will get a value. Simply I write it in this decimal format, right? This will be 1. Then minus 1, right? So the value equivalent for all 32 bits 1. This is, let me write here itself. This is equal to minus 1. So during the 31st bitwise right shift operation, what happens means surprisingly all 32 bits are set to 1 and we have a value minus 1. So check the result here. J is equal to 31. We have printed a value y greater than 31. Value becomes minus 1. Hereafter, right, if you perform right any number of times, right, J is equal to 32, 33, 34, 35, etc. Right? What happens? You will get the same value, right? All bits are ones. That is the indication of a minus 1. You try to check, right? Some additional exercises like this. So this is the purpose of a bitwise right shift operation. This is completely opposite to bitwise left shift operation. Here, each time the value of a variable is divided by 2. That is very important. And this the right shift operator keeps the sign during each bitwise right shift operation. That's what this is said to be a sign extension operator. So sign is retained. 1 plus plus minus minus. What we have said, the value is divided by 2. Initial value of x is positive. So when this is divided by 2 in the subsequent shifts, the sign should be positive. So here positive, positive, etc. Here the initial value of integer variable, say y is a negative 1. Every time you are performing divide by 2 operation, subsequent numbers should be a negative quantity. So finally, right, till reaching a value minus 1, the quantity, right, are all quantities are all a negative 1. So the bitwise right shift operator retains the sign during each right shift operation. In some applications, it is necessary to set right the most significant bit as 0. Sign extension is not necessary in some applications. For that purpose, Java specially defined one kind of operator called right shift operator with 0 fill. The operator is greater than greater than greater than. It is termed right shift operator with 0 filling, or simply the unsigned right shift operator. This will not keep the sign in the subsequent operation. Greater than operator is a sign extension operator. Triple greater than operator always shifts zeros into the higher order bit. So new MSB 0 is brought or 0 is set during each unsigned right shift operation. For this, right, let me explain through this code. Int x is equal to minus 1, right? You know how minus 1 is represented in a 32-bit register, because here x is the integer variable. Minus 1 means x is equal to minus 1. The equivalent encoding is all 4 bytes are set to 1. Very simple. Okay. All 32 bits are set to 1. Now what are we going to do? We are performing the bitwise right shift operation on the operand, right, integer operand x is equal to minus 1. So as usual, right shift, that is the value of j. Here let us have the column x triple greater than j. No typecasting because x is the integer operand. Then shift is 0. The value of x greater than j is say minus 1. And shift is 1. Here what happens? You consider the first 31 bits. First 31 bits are moved one position to the right direction. So here this is the effect. And this LSB 1 is lost. What about the new MSB? New MSB is
0, sir. 0. 0.
yeah, very good, because of this operator inserts a 0 into the new MSB position. Then shift number 2. In shift number 2, consider the first 31 bit positions. First 31 bit positions are moved one position right. So last one LSB is lost. New MSB 0 is added. So this is the result during the second shift operation. Then third operation. Control C. Okay, let me write a few values. What happens here? Third bit becomes 0. Then during the fourth unsigned shift right operation, first 4 bits are set to zeros, etc. During the 30th shift, what happens? Need to write, right? Okay. 1, 2, 3, 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Then 30. 1 means how many zeros are there? 1 zeros. Carefully look here. 2 means 2 zeros are there. 3 means 3 zeros. 4 means 4 zeros. So during the 30th shift, how many zeros are there? 30 zeros.
30 zeros.
Means
30 zeros.
16 24 1 2 3 4 5 6 then what one am I right? Successfully pieces, right? Then 31st operation, let me copy and paste. 31st means 31 zeros will be here 0. Then 32nd shift unsigned right shift operation, all 32 bits are set to zeros. This is 0 and the next bit is 0. Then subsequently you can perform any number of bitwise right shift unsigned right shift operation on the operand. X is equal to -1 here. Continuing to this value, you will get the quantity 0. So let us check the result. What is our code? I think class operator 7. Java C operator 7.java. Java operator 7. -1, we are performing for how many number of times? 35 times. Bitwise right shift operation with 0 link. But look the result initially -1, then this quantity 2 1 4 7 4 8 3 6 4 7 that is correct. Then the values are halved divided by 2, then 30 31 31 is right. 31, what is the value? 1. 31, what is the value here? 1. Then 32nd shift, actually what happened, x becomes -1. This is not 0. You need to justify how -1 is coming. So I am leaving this question to you. You need to answer. Thirtieth shift, right? Value 3. This is 3. 1 plus 2, 3. 31st shift 1. 32nd shift. 31st shift 1. 32nd shift, right? I have programmed, right? Check the code here. J ranges from 0 to 35. X is equal to x greater than j. That's all. So the program prints the value x is equal to -1 during its 32nd bitwise unsigned right shift operation. But here this 1 is performed right there one more time. What happened? This is not 0, but the value is reaching this quantity -1. How? Okay, you have to check and answer me later. Now I am moving on to the next operator. Operators, some Boolean and logical operators and relational operators. Now coming to this topic, relational operators. Similar to C and C++ languages, Java supports some relational operators, less than, greater than, less than or equal to, greater than or equal to. Then this is not equal to operator, and this is equal to operator, conditional equal to operator. The result of a relational expression formed by using the relational operators results in a Boolean value, either true or false. For example, int x is equal to 100, y is equal to -100, Now Boolean b is equal to x less than y means x is greater than y. So here the variable b holds a value false. So the result of a relational expression formed by using the relational operators is either true or false. But when you use these operators, right, not equal to and equal to operators, this is different in Java. Since Java, there is no such concept of any non-zero values are taken as true and other values are taken as false from C and C++. Will not hold in Java. For example, in C and C++, these lines of code are okay. Int x, if x, then some block of statements. If not x, some block of statements. This is valid because here it checks the value of x. If x is 0 or non-zero. If x is a 0, that is taken as a false quantity, condition becomes false. Any non-zero value is taken as a true, including negative quantity. Where in Java, these lines of code will not work. Explicitly, the user must specify using the relational operators not equal to or is equal to. So you need to write explicitly checking if x is not equal to 0 or check if x is equal to 0. This kind of explicit checking is to be done in Java language since Java does not support this concept of right true and false with respect to any non-zero value and zero value because in Java Boolean data type is supposed the Boolean values only, right? True or false. Understand or not? The remaining operators are same as that of C and C++ languages, greater than, less than, greater than or equal to, and less than or equal to. We can use these relational operators to form an expression called a relational expression. Then operators 9. Boolean logical operators. These are of course right, polymorphic operators. We have seen these operators in bitwise operation. Think of that one's complement, bitwise and bitwise or pipe symbol, bitwise exclusive or. The same thing, right, can be written using the shorthand assignment operation, right? Not equal to, or then ampersand equal to, not or symbol is equal to, XOR is equal to. Then this is the conditional equal to, right, with respect to Boolean logical expression. Then these are right some special operators. These two are special operators. Double ampersand, then double or are said to be. These are said to be conditional or conditional and conditional or. That is short circuit logical operators. In case of short circuit logical operators, the result is evaluated in a different way. You know, previously, right, these operators are applied in the bitwise expressions, bitwise operands. X is equal to, so for example, integer operand 10 and 20. 10 should be written in a binary form, or 20 should be written in a binary form, and compare the bits. If both bits are 1, then the result is 1. If any one bit is 0, the result is 0 in case of bitwise AND. But in case of Boolean logical operation, here you need to write x is greater than 5 and x is less than 10, right? So x greater than 5 means this results in a Boolean value either true or false, and x is less than 10, say that results in a Boolean value either true or false. So the result of Boolean logical expression is either true or false. So these operations can easily be returned. Ampersand, right? Boolean logical and logical or and Boolean logical XOR, and this is Boolean logical NOT. Here this Boolean logical NOT negates the true value into false and the false value into true. Now have a look into right these special operators, conditional and conditional OR operators. In case of conditional and conditional OR are concerned, right, based on the evaluation of one operand, one operand is the left hand operand. If the left hand operand is alone to determine the value of that Boolean logical expression, right hand operand will not be evaluated. That is a additional feature of or special feature of these short circuit logical operators, conditional and conditional or. Just to have a look into these lines of code so that you can easily understand the purpose of conditional and conditional or. Consider these lines of code. X is 5, y is 6, z. Z is equal to x ampersand y. This is simply the bitwise and the operation on the operands 5 and 6. You try to write a 5 in a binary form, say in a 32-bit register, and represent 6 in a 32-bit register, and perform the bitwise and operation on the operands x and y, and find the equivalent quantity that is stored in a variable z with respect to the integer form. Right? So this is not a new one to you, right? Already we have seen the bitwise and operation. In the same way we can do the trees. Now have a look into these two lines. Boolean b is equal to x greater than y, short circuit and some expression we have written. Relational expression is written. In this case, what happens? What about x greater than y? X greater than y means 5 greater than 6. What is 5 greater than 6? 5 greater than 6 is false. Here, this is a left hand operand. This is operator, short circuit logical and operator or conditional and operator, and this is the right hand operand. So the result is based on the left hand operand and the right hand operand. If any one is false, the result is false. If both are true, then the result is true. But short circuit logical and, that is conditional and, is concerned, left hand operand is evaluated first. If the left hand operand determines the final result of this logical and expression, right hand operand will not be evaluated. This is very important function. X greater than y means x is 5, 5 greater than 6 condition is false. So the total result of a Boolean variable b is false without evaluating the right hand side expression. Carefully look into the right hand side expression what we have written. X division y minus y. Y is of course 6, whatever the value of y. Y minus 5, y minus y becomes 0. Something by 0 will not be evaluated, right? This results in the arithmetic exception, runtime error, right? So without reporting the runtime error, logically, right hand operand is not evaluated. Only the left hand operand is evaluated x greater than y. Since this determines the value of entire expression, right hand operand is not evaluated. So the value of a Boolean variable b is set to false. Let us check the code. Java operators 9. First line, right? Z is equal to 4, right? You try to do the trace, you will be getting the value Z is equal to 4 in the bitwise AND operation. Now have a look into this expression, x greater than y and this one. So it seems that the highlighted expression is not evaluated because x greater than y becomes false. That determines the final result of a Boolean variable. So the second line we can find out the result b is equal to false. Likewise, carefully look into these two lines of code. In this case, the Boolean, right, a short circuit logical OR is introduced. Conditional OR is introduced. This is operand 1, x less than y. Operand 2 is x division y minus y is greater than x plus y, right? That's of course a relational expression. This is also a relational expression. Now x less than y means 5 less than 6. Condition is true. True or something, right? Whatever the result of second one, true or false, the final result is true. So logical or short circuit logical or is concerned. The left hand operand determines the result of final expression. Then right hand operand will not be evaluated. In this case, right, we have the value b is equal to true. Hope you understand. Then considering the last two lines of code here, what happened? Logical AND is introduced. What is logical AND? Short circuit logical AND. But unexpectedly, x less than y. X less than y becomes true. Hope you understand. 5 less than 6 becomes true. So true under something, the second operand may result in a false, right? So without evaluating the second operand, the short circuit logical AND will not conclude the result. This case, it is necessary to evaluate the right hand operand. So right hand operand is because left hand operand is true. True and only the result is determined based on the right hand operand. Right hand operand is true, then the result is true. In case right hand operand is false, because true and false results in false, right? So when evaluating the right hand operand, carefully look into this arithmetic. Y minus y, x is and y minus y. This results in a runtime error, not a compile time error. So you can see the message, this one, during the runtime. Exception entered java.main.java.lang dot arithmetic exception. Arithmetic exception is the error name in which the divide by zero operation, divide by zero error, right, or operation is defined. So the last line here, b is equal to results in a runtime error. So the purpose of the short circuit logical operators are left hand operand is evaluated this. If the left hand operand determines the final result of the short circuit logical expression, right hand operand will never be executed. That is the rule. Then the last code, 2 minutes, let me complete. Assignment operator, right? This takes this general form variable is equal to expression semicolon, similar to C and C++ languages. Then you can declare some variables and you can initialize the same value to multiple variables. Multiple initialization is permitted. The value of q, right, character is first set to a variable z, and then the value of z is set to a variable y, and then the value of variable y is set to a variable x. So ultimately, all these character variables x, y, and z are assigned a character constant. Then one more operator, ternary operator, a conditional operator similar to that of C and C++ languages. Expression 1, then expression 2 colon expression 3. Expression 1 is evaluated first. If it results in a true, right? Expression 2 is evaluated. Suppose if this results in false, expression 3 is evaluated. For example, checking if x is greater than 0. This line is perfectly valid. Extra parenthesis not necessary. Checking if x is greater than 0, then the quantity 0 is assigned to the left hand side variable result. If x is equal to 0, results in false, then x by y is evaluated, and this expression x by y, result of expression x by y is set to be a left hand side variable result. So there is no new thing in the conditional or ternary operator, same behavior of C and C++. Then finally, the very important one, whenever we are using the set of operators in Java, we need to understand the precedence, priority, right? How the expressions are evaluated. Expressions inside the inner parenthesis is evaluated first, then outer parenthesis, then outer, this way, from inner to outer. Then in all these cases, expressions are evaluated from left to right rule, right? When multiple operators are having same priority, the precedence, the expressions are evaluated from left to right rule. So above all, we have to recall that the operator precedence table is given in the book, right? Try to follow that. Plus plus minus minus, that is the postfix. Plus plus or postfix minus minus, x plus plus x minus minus takes the highest precedence, and finally, right, here we can have the is equal to operator. Lowest precedence is equal to operator. Highest precedence takes x plus plus or x minus minus, simply the postfix operator, plus plus minus minus. Parentheses are also important. Whenever we want to introduce the proper parentheses, in that way the expressions are evaluated. Missing the parentheses, sometimes unexpected results may occur. But as far as possible, try to include the parentheses if it is necessary. The expression is very ambiguous to understand, right? then that situation you try to include the parenthesis properly. In the first case, x double less than y plus 5 means y is added with the quantity 5 and then performed bitwise left shift operation. X is performed bitwise left shift operation y plus 5 times. Same is given in number 2, x less than y plus 5. Parenthesis is extra introduced, right? Introducing the extra parenthesis here, one can easily conclude that add y with 5 and then perform bitwise left shift operation. Here the concept is less than and plus, which takes the first precedence means plus takes the first precedence. So y plus 5 is evaluated and then x less than that the result is evaluated. Likewise, the third one, in case if you put parenthesis here, x less than y plus 5 means x is performed bitwise left shift operation y times and the result is added with 5. That is the mean. A fourth one, a, this is or, a or 4 plus c greater than b and 7. This is perfectly valid expression in which this plus operator takes first precedence, 4 plus c, then greater than operator. 4 plus c is evaluated with greater than b. So 4 plus c is evaluated and performed bitwise right shift operation b times. And then the logical and, sorry, this is not a logical and, what one? Bitwise and 7 is one integer. Here you will get one integer. Then bitwise and operation is carried out. After that, this one, what is this one? Or, bitwise or operation. Bitwise not and or, right? Logical not and or, that is the order. So here and is evaluated first and then r is evaluated. So 4 and 5 perform the same rule, but to avoid the confusion which operator is executing first and which is next, it is better to write 4 in terms of 5. But 1 and 2 are also same. If you are not clearly understand, this is the plus takes more precedence, then using extra parenthesis will not be a problem. With this we are completing
Sir, between
the
and bitwise or right shift so between bit
What on?
or and bitwise and the right shift operator has more precision, sir.
Bitwise right shift operator.
Yes, sir.
You please go through the table, right? Operator precedence table is there, in which the first precedence, second precedence, third precedence, etc. are given. Here, more than one operators are available at the same level. In that stage, operations are evaluated from left to right. For example, the plus, minus, right, are all taking same precedence. Star, slash takes same precedence, but the operations are evaluated from left to right. For example, a plus b minus c. A plus b is evaluated first because plus and minus take same precedence, and then the result is performed right with the operation minus c. Likewise, x star y division result. Division and multiplication take same precedence. Both are same. Dividing right y by z and multiplying the result with x, right? Same as x star y. X is multiplied by y first, and then division operation is carried out because left to right. Left to right means star is evaluated first. Here plus is evaluated first. So you please go through the operator precedence table. Based on that, the expressions are going to be evaluated. And above all, expressions inside the inner parenthesis is evaluated first. That is important rule. You might have studied, right? Boardman's rule. Bracket expressions inside the inner parenthesis. Even more operators are taking same precedence inside the inner parenthesis. Then there you need to apply the left to right. Having any other queries? The next session I will focus on introduction to control statements and then we are directly entering into the core part of Java. How to define the user-defined classes, right? Methods, how to create objects. That is very important. The core part of Java. So the next session we focus on the control statements along with the classes and objects as the core part of Java. Any other queries? I have asked one question right during the session. I will try to recall that. I have deleted it, cleared the screen. You go through this that code. I think operators 8.java. I think not 8. Sorry, 7.java. I raised one question. 32 bitwise right shift operation, unsigned right shift operation. How this one is changed to -1. You might have recalled that, but actually 0 is the mean. You need to answer this question. So please go through, I post the videos and the corresponding Java files, go through these things and go through the complete reference to the operators chapter. Uh, you can raise your queries. I will clear your doubts. Having any other queries? One of the answers asked to these questions are how 1 followed by 3106 is quantity. I explained in the video session. 1 is the indication of a negative number. So remaining 31 zeros should be decoded in 2's complement format. So you will get this quantity, negative quantity.
Sir, if we convert all the other 31 zeros into 1 and add 1, then everything becomes 0 again.
Not zeros. You need to consider that the 32nd bit position also. Including that value, you need to consider the minus sign, minus negative of that 2's complement equal. We go through the text Java file, and if you find any other queries, you ask me, I will explain. Okay, now let us wind up the session. Thank you very much.
Thank you, sir.